Hey guys, today we are going to discuss on the topic floating point arithmetic, coprocessors and pipeline processing, presented by Abhinav Singh, Guru Prakash A and Vivekanandan G. Floating point arithmetic. It is represented as xm into b to the power xc, where xm is mantissa and xc is exponent and b is base. Four basic arithmetic operations for numbers are addition. Let's take two variable x and y. Xm into 2 to the power xe plus ye plus ym into 2 to the power ye. Subtraction. X minus y is equal to xm 2 to the power xe minus ye into ym into 2 to the power ye. Multiplication. X into y is equal to xm into ym into 2 to the power xe plus ye. Division. X by y is equal to xm by ym into 2 to the power xe plus ye. Now let us see some examples for floating point arithmetic, or you can say numbers. Examples for floating point numbers in base 10 are 5.341 into 10 to the power 3, 0.05341 into 10 to the power 5 minus 2.013 into 10 to the power minus 1 minus 201.3 into 10 to the power minus 3, where 10 represents the decimal point. Examples of floating point numbers in base 2 are 1.00101 into 2 to the power 23, 0.0100101 into 2 to the power 25 minus 1.101101 into 2 to the power minus 3 minus 1101.101 into 2 to the power minus 6. Here 1 and 0 represents the binary point. Exponents are kept in decimal for clarity. The binary number 1101.101 base 2 can be also written as 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0 plus 2 to the power minus 1 plus 2 to the power minus 3, which is equal to 13.625. Floating point number should be normalized. Exactly one non-zero digit should appear before the point. In a decimal number, this digit can be from 1 to 9, but in a binary number, this digit should be 1. Normalized FP numbers 5.341 into 10 to the power 3 and minus 1.101101 into 10 to the power minus 3. Not normalized numbers 0.05341 into 10 to the power 5 and minus 1101.101 into 2 to the power 6. Now let us move to our next topic, floating point addition, subtraction, flowchart. First, we have to compare the exponents of two numbers. Shift the smaller number to the right until its exponent would match the larger exponent. Add, subtract the significance according to the sign bits. Normalize the sum, either shifting right and incrementing the exponent or shifting left or decrementing the exponent. Round the significand to the appropriate number of bits and renormalize if rounding generates a carry. Now let us check whether the output is overflow or underflow. For yes, it's an exception. No, it's done. Here are some notes that we must follow during this algorithm. Shift significand right by d is equal to ex minus ey, where ex and ey are exponents. Add significand when sign of x and y are identical. Subtract when different, x minus y becomes x plus minus y. Normalization shift right by 1 if there is a carry, or shift left by the number of leading zeros in case of subtraction. Rounding either truncates fraction or adds 1 to least significant fraction bit. Now let us move to algorithm of multiplication or division. Start. Add or subtract base component of two numbers, subtracting the base from sum to get the new base exponent. Multiply or division the significand. Set the result sign to the positive if operand have same sign and negative otherwise. Normalize the product if necessary, shifting its significand right and incrementing the exponent. Round the significand to the appropriate number of bits and renormalize if rounding generates a carry. Again, we have to check whether the output gives an overflow or underflow. Yes is an exception. Now we get the output. Some of the basic notes are biased exponent addition or subtraction, Ez equal to Ex plus Ey minus bias. Result sign Sz equal to Sx, XOR Sy can be computed independently. Since the operand and operand significand Fx and Fy are greater than equal to 1 and less than 2, their product is greater than 1 and less than 4. To normalize solution, we need to shift right or left by one bit only and increment or decrement the exponent. Rounding either truncates fraction or adds a 1 to least significant fraction bit. Now let us move to our next topic, that's guard bit. When we shift bit to the right, those bits are lost. We may need to shift result to the left or for normalization. Keeping the bits shifted to the right will make the result more accurate when result is shifted to the left. Let's see the question which should arise in this topic. Which operation will require shifting the result to the left, and what is the maximum number of bits needed to be shifted left in the result? If the number of the right shift for alignment is greater than 1, then the maximum number of left shift required for normalization is 1. Now let us move for the steps which should be taken for effective addition. Result of addition should be either normalized or generates one additional integer bit. Hence, right shift of 1 need for f plus 1 bits. Extra bit called rounding bit is used for rounding the result. Alignment throws a bunch of bits to the right. Need to know whether they were all 0 or not for proper rounding. Hence, one more bit called the sticky bit. Sticky bit value is the OR of the discarded bit. Now for an effective subtraction, we should follow the following steps. There are two subcases. If the difference in the two components is larger than 1, alignment produces a mantissa with more than 1 leading 0. Hence, result is either normalized or has 1 leading 0. In this case, a left shift will be required in normalization. An extra bit is needed for the fraction called the guard bit. Also, during subtraction, a borrow may happen at position f plus 2. This borrow is determined by the sticky bit. The difference of two exponents is 0 or 1. In this case, the result may have many more than 1 leading 0, but at most one non-zero bit was shifted during normalization. Hence, only one additional bit is needed for subtraction result. Borrow to the extra bit may happen. Floating point complexities. There are many reasons why these are not, so in common people. They are operations are somewhat more complicated. In addition to overflow, we can have underflow. Accuracy can be a big problem. Extra bits to maintain precision, guard, round and sticky bits. 4 rounding modes. Division by 0 yields infinity. 0 divided by 0 yields not a number. Other complexities. Implementing the standard can be tricky. Not using standard can be even worse. Now, the next topic, coprocessors, will be taken by Mr. Guru Prakash. Thank you.
Thank you, Mr. Abhinav Singh. Now we are going to see about coprocessors. Coprocessors are a set of instruction set coprocessors that is closely coupled to CPU. It is an alternative design of auxiliary coprocessors that provide fast, low-cost hardware implementations. Instructions executed in transparent manner. It is used for tasks such as managing the memory system or controlling graphics devices. This is the connection between CPU and coprocessor, which is connected through system bus through several channels. It consists of decoder, interrupt request, synchronization signals, and the main connection from system bus is given to main memory and IO devices. Its operation is basically the instructions of coprocessor can be included in machine code manner. It requires specialized control logic to link the CPU with the coprocessor. To CPU, the coprocessor is actually a passive or slave devices. The communication between CPU and the coprocessor is to initiate and terminate the execution of coprocessor instructions that occurs automatically as a coprocessor instructions are encountered. Even in absence of coprocessor, its instructions can be included in CPU programs. This type of CPU generated interruption of normal program flow is called coprocessor trap. Thus, the coprocessor provides both hardware and software support for certain instructions without altering the source or object code of the program. Coprocessor instructions contain the three fields F0, F1 and F2. F0 indicates the difference between the instructions, and F1 indicates the address of particular coprocessor, and F2 is the operand addressing information. Now let's see the merits and demerits of coprocessors. Coprocessors usually increases the speed of the system bus. It can use to execute instructions directly in absence of CPU. Demerits: unlike CPU, it cannot analyze contents of the register defining the current memory addressing modes. So half decoding is done by coprocessor and another half by central processing unit. Now the rest will be taken by Mr. Vivekanandan.
Thank you, Mr. Guru Prakash. My name is G. Vivekanandan. I am going to talk about pipeline processing. Pipeline processing is a general technique for increasing processor throughput without requiring large amount of extra hardware. It is applied to design of complex data path units such as multipliers and floating point adders. Okay, we are going to start introduction part of the topic. Your pipeline processor consists of a sequence of M data processing circuits called stages or segments, which collectively perform a single operations on a stream of data operands passing through them. Some processings takes up place in each stage, but a final result is obtained only after an operand set has passed through the entire pipeline. As illustrated in the figure, a stage SI contains multi-word input register or latch array and a data bus circuit CA that is usually combinational. The arrays hold the partially processed results as they move through the pipeline. They also serve as buffers that prevent neighboring stages from interfering with another. At first sight, a pipeline seems too costly and slow, but it way to implement the target operations. Its advantage is that M stage pipeline can simultaneously process up to M independent sets of the data operands. These data sets move through the pipeline stage by stage, so that when the pipeline is full, M separate operations are being executed concurrently, each in a different stages. Then we are going to talk about pipeline design. Pipeline design. Designing a pipeline circuit for the function involves the first finding a suitable multi-stage sequential algorithm to compute the given function. The algorithm steps which are implemented by the pipeline stages should be balanced in the sense that they should all have roughly the same execution time. Fast buffer registers are placed between the stages to allow all necessary data items to be transferred from the stage to stage without interfering with one another. The buffers are designed to the clocked at the maximum rate that allows data to be transferred reliably between the stages. This is the pipeline version of floating point adder. In this figure shows the register level design of a floating point adder pipeline based upon the non-pipeline design and employing the 4-stage organization of figure. The main changes from the non-pipeline case is the inclusion of buffer register to define and isolate the 4 stages. The further modification has been made to implement the fixed point as well as the floating point addition. The circuit that performs the mantis addition in the stage S3 is, and the corresponding buffers are enlarged as shown in the broken lines in figure to accommodate full-size fixed point operands. To perform a fixed point addition, the input operands are routed through the S3 only. By passing the other 3 stages, the circuit of the figure is an example of the multifunction pipeline that can be configured either as the 4-stage floating point adder or a 1-stage fixed point adder. Thank you guys. That's all about the pipeline.